In this video, we are going to be doing an introduction to probability. So just some of the basic ideas that you can use throughout the unit on probability. So first we want to talk about experimental probability versus theoretical probability. So experimental probability is based on observations or experiments that are actually performed. So an example would be rolling a fair die 1,000 times and recording how many times each number appears, and then using that information to calculate the probability of rolling a specific number. So you're actually using real data to calculate a probability based on that data. So to calculate a probability of an event, in this circumstance, you would look at the number of times that an event occurred, and then you would divide that by the number of observations made in total. So here's an example. Find each of the following probabilities. Write your answer as a reduced fraction or a decimal rounded to the nearest thousandth. Generally in your homework it'll tell you one or the other, but you can write your probabilities in either fraction form or decimal form. So a group of students were asked if they had attended any of the baseball games played on campus. 234 students said, "No, I have not attended any baseball games," while 109 students said, "Yes, I have attended at least one baseball game." Part A is find the probability that if a student is chosen at random, the student did not attend a baseball game. All right, so we have no, I didn't attend a game. That's 234. And we have yes, I attended a game, and that's 109. So we can find the total number of students because we need that. That's the denominator. So we can find the total number of students by adding 234 to 109. When we add those together, so 234 plus 109, we get 343. So that's going to be our denominator. Find the probability that if a student is chosen at random, the student did not attend a baseball game. So 234 said they did not attend. Out of 343, so that would be your fraction. Now, that might not be in reduced form. If you're not sure if it's in reduced form and you have the option to put it in decimal form, that's what I would do. So you would just divide 234 by 343. And we want to round it to the nearest thousandths. That is 3 numbers after the decimal. So 0.682. Remember that fractions, decimals, and percentages are interchangeable, right? You can write them in all 3 forms. So any of those would be correct. Of course, this time the directions didn't give you the option for percentage, but if it did, that would be the percentage associated with that decimal and with that fraction. So approximately 68% of the students have not attended a game. So if you selected one at random out of these 343, the chances are 0.682 exactly that they have not attended a baseball game. All right, part B, find the probability that if a student is chosen at random, the student has attended at least one baseball game. So that's 109 said that they had attended a game out of the 343. And so we would do that division, 109 divided by 343, and we would get, well, let's do a 0.318. So that's approximately 31.8%. Okay, notice that if we add 0.682 plus 0.318, we get exactly 1. These are called complementary events. There are 2 things that could happen. Either they have attended a game or they have not attended a game. In total, that should be 1 because that's 100% of the students. Right? So these are called complementary events. A complementary event is one in which something does not happen. So you could say the student did not attend a baseball game is complementary to a student did attend a baseball game. So 1A and B, and this is mislabeled here. That should be 1A and 1B are complementary events. The probabilities for complementary events always add up to 1. Okay, so that was experimental probability. Now we're going to talk about theoretical probability. So a theoretical probability is based on what could possibly happen. And you're always kind of looking at equally likely outcomes. Well, not always, but generally that's what we're going to base our information on. If they're not equally likely outcomes, then you would have to make adjustments for that. And we're not going to get into that. So a theoretical probability is, an example would be if you have a fair die with 6 sides, each side is equally likely to be rolled. So if you know that there are 6 sides and each side is equally likely to be rolled, then you can say there's 1 out of 6 chance that each of the numbers gets rolled. Now in reality, if you roll the die, it's probably not going to happen to where you get exactly the same number of every number. That's what happens when you do experimental probability. But in theory, we know that each number has the same chance of being rolled. So the probability of an event occurring when you're talking about theoretical probability is the fraction for the number of ways an event can occur on the top and the number of total possible outcomes on the bottom. This sample space is going to be referred to throughout some of the lessons that you'll see on probability. That's the set that includes every possible outcome. So the sample space for rolling a fair 6-sided die would be 1, 2, 3, 4, 5, 6. That's all the possibilities. A sample space for flipping a coin would be heads or tails. So that sample space would only include 2 elements, heads, tails. So probabilities must be between 0 and 1, or 0% and 100%. The probability of 0 means that the event is impossible. There's no way that it could happen. A probability of 1 means that an event must occur. So there's no chance that it will not happen. So if you say there's a 100% chance, that means it is definitely going to happen. There's no question. The closer the decimal or fraction or percentage is to 1 or 100%, the more likely it is that that event will occur. So let's look at some more examples. Find each of the following probabilities. Write your answer as a reduced fraction or a decimal rounded to the nearest thousandth. Okay, so we're going to roll a fair 6-sided die 1 time, and we want to do the following. So first, find the sample space. So the sample space is the set that includes every possible outcome. So one possible outcome is we roll a 1. Another possibility is that we roll a 2, or a 3, 4, 5, or 6. So that's the sample space. Part B, we want to know what the probability is. What is the probability that we roll a 3? So there's only one way to roll a 3, and there are 6 possible outcomes. So the probability would be 1 over 6. That fraction is in lowest terms, so you can leave it like that, or you can actually do the division, 1 divided by 6, and round your answer to the nearest thousandth, which is 1.167. Okay, I want to know the probability that you roll a 6. Well, there's only one 6, and there are 6 possible options when I roll. So the probability of rolling a 6 is the same as the probability of rolling a 3. It's 1/6. I'm just going to go ahead and use fractions for the rest of these, but know that you could put it in decimal form by just dividing. Part D is the probability of not rolling a 6. Of not rolling a 6. So this is complementary to C. So C is the probability of rolling a 6, and D is the probability of not rolling a 6. So you either roll a 6 or you don't. Remember that complementary events must add up to 1. So if you use that to your advantage, you know that 1 minus the complement will be your answer here. So 1 minus 1/6 is 5/6. Alternatively, you can just figure out that not rolling a 6 is the same as rolling a 1, 2, 3, 4, or 5. So there are 5 possible outcomes that are good out of the 6 total options. So either way, you would get 5 out of 6. Okay, part E is the probability that you roll a 7. So if we look at our sample space, we can see that 7 is not listed. So that probability is 0. So you cannot roll a 7 because that's not one of the numbers on the die. Part F is find the probability that you roll a 2 or a 3. So a 2 or a 3, that's 2 things that are good out of 6 possibilities. You want to make sure you reduce your fraction, so that would reduce to 1/3. Okay, part G is you roll an even. So if you go back and think about your sample space, I will write it over here. And I'm looking for even numbers. So that's a 2, 4, and a 6. So there are 3 numbers that would be even. There are 6 possible numbers to choose from. So 3 out of 6 would be the probability of rolling an even, and then I would reduce to 1/2. Okay, probability of rolling a number greater than 3. So numbers greater than 3, that would be 4, 5, and 6. So there are 3 numbers greater than 3 out of 6 possible numbers. So again, I reduce and get 1/2. So again, notice that we're putting the probability, or to find the probability, we're putting the number of outcomes that you want. So the desired outcome on top. And on the bottom is the total number of possible outcomes. All right, part I, find the probability that you roll a number less than 8. So if I look at my sample space, all of these numbers are less than 8. So that would be 6 desired outcomes out of 6 possible outcomes. So that would be a 1. So you're definitely going to roll a number less than 8. Okay, another popular topic in probability. So dice is one. Sometimes you roll 1 die, sometimes you roll 2 dice, and they'll ask you questions about that. Another thing they like to ask questions about is cards. So they'll tell you that you have a standard deck of cards, and you might draw 1 or more cards from the deck, and they'll give you specifics about the card or cards that you're drawing, and you'll find the probability of doing so. So if you're not familiar with cards, so some people are very familiar with cards and they don't need a visual, but here is a visual in case you need it. So you can see that there are cards, we have an ace, usually that's considered a 1, but sometimes it's considered the high card above the king. You have the numbers 2 through 10, and then you have the face cards, jack, queen, and king. So there are 3 face cards, 3 different kinds of face cards. You have 4 suits, so you have spades, hearts, diamonds, and clubs. And each card is represented in each suit. So there are 4 10s because there's 1 10 of each suit. So that's the same for all of the cards. There are 13 cards in each suit. So if you look ace through king, those are 13 different cards. So refer to this as needed. All right, so here are some questions about the cards. So one card is selected from a standard 52 card deck. Find each of the following probabilities. So part A, find the probability that the card is an ace. So there are 4 aces, if you look at your visual above, 4 aces, so that's the desired outcome, that you get an ace. And the total possible outcomes, or the total possible options, there are 52 cards. So 4 out of the 52 cards are aces. If you reduce that fraction, that would be 1 out of 13. Okay, part B is the card is a face card. So the face cards are Jack, Queen, and King. So if you look at the visual above, you will see that there are 4 Jacks, there are 4 Queens, and there are 4 Kings. So there are 12 face cards out of 52 cards. And so then you could reduce this fraction. Let's see, you can reduce them both by 4. So 12 divided by 4 is 3, and 52 divided by 4 is 13. So 3 out of 13 is the probability that you draw a face card. Part C, find the probability that the card is not a face card. So notice that part B and part C are complementary events. So they're complements, because B is that it is a face card and C is that it is not a face card. It's one or the other. So remember, if you want to use the rule about complements, these two must add to 1. So you can do 1 minus 3 over 13 to get 10 over 13. So the answer to this one is 10 over 13. Alternatively, you can look at your sample space, which is the visual above, and count all of the ones that are not face cards. So you would see that you have 10 in each suit, so that would be 40. So 40 cards are not face cards out of the 52. And then if you divide by 4, you get 10 out of 13. So the same thing either way you look at it. Okay, part D, find the probability that the card is a heart. So if you look above, you'll see there are 13 cards that are hearts. So there's 13 of each suit. So 13 hearts out of 52 cards. And if you divide by 13, you'll get 1/4. E, find the probability that the card is not a heart. Again, notice that D and E are complements. It's either a heart or it's not a heart. It's one or the other. Those are complements. So you can take advantage of the rule of complements and do 1 minus 1/4, and that would be 3/4. Or you could just go up and look at your visual and count how many are not hearts. So if 13 are hearts, then you can do 52 minus 13, and you will find that 39 are not hearts. So 39 out of 52, and you can divide both of those by 13 to get to your lowest terms, which is 3/4. Okay, part F, find the probability that the card is a diamond or club. Okay, so there's different things that could happen here. There are 13 diamonds and there are 13 clubs. And those do not overlap, right? If it's a diamond, it cannot be a club. So we have 26 outcomes that are favorable out of 52 cards. And both of these are divisible by 26, and we'll see that we get 1/2. All right, part G. Find the probability that the card is a heart or a 5. Now I want to go ahead and go up to the visual so I can point something out. I want to know the probability that the card is a heart. So that's all of these, right? It could be any of these. So that's 13. So there are 13 hearts. Okay, or a 5. Let's go up and look at the 5s. So, or a 5 would be any of these. But do you see that the 5 of hearts is being counted twice? The 5 of hearts is a heart, and it's also a 5. So you have to be really careful here. You want to count the 5s that haven't been counted yet. So if you count the 5 of hearts as a heart, you don't want to count it again. So there would be 3 other cards that would be counted, which is, 3 more. So there are 4 5s, but the 5 of hearts has already been counted as a heart. So you would not count it again, or you would have a problem. So that would be 16 cards that are favorable out of 52. And you can divide both of those by 4, and that would give you 4 out of 13. So be really careful with these ors. Make sure that they don't overlap. So diamonds and clubs do not overlap. You can't have both of those things at the same time. But a heart and a 5 can overlap because you have a 5 of hearts. And so you don't want to double count. Okay, if we see part H, we want to know the probability that the card is the Queen of Hearts. Well, if we look at our visual, there's only one Queen of Hearts. There's other queens, but they're not the Queen of Hearts. So the probability of drawing the Queen of Hearts is 1 out of 52 cards. All right, number 4. 2 cards are selected from a standard 52 card deck. Find each of the probabilities. So in number 3, we were only drawing 1 card. Now we're going to be drawing 2 cards. So let's see how that kind of changes the scenario here. Both cards are spades. So you want to find the probability of each card being a spade. So the probability of the first card being a spade is 13 out of 52 because there are 13 spades out of 52 cards. But after you get that first card, that card is gone, and the second card, there's only 12 spades left because you're assuming that you got a spade, and there's only 51 cards left. So 13 over 52 is the probability of that first card being a spade. And then once you take that spade, there are only 12 spades left. And since you've taken a card, there are only 51 possible cards left. So you will multiply those together to get the overall probability. So if I multiply 13 times 12, I will get 156. And 52 times 51 will give me 2,652. That is not in lowest terms, so to avoid not reducing it all the way, I'm just going to go ahead and write it as a decimal, rounded to the nearest thousandth. So 156 divided by 2652. So rounded to the nearest thousandth would be 0.059. All right, part B. Find the probability that the first card is a heart and the second card is a spade. So the first card is a heart. There are 13 hearts and there are 52 cards. The second card is a spade. So we haven't taken a spade yet. We've taken a heart. So there are still 13 spades, but we did take a card. So there are only 51 cards to choose from now. And so when we multiply that together, we will get our probability. So 13 times 13 is 169. 52 times 51 is 2652. And then again, in order to make sure I don't miss any points here, I'm going to just go ahead and write it as a decimal. So that will be 0.064. So that would be the probability that the first card is a heart and the second card is a spade. All right, part C, find the probability that both cards are jacks. So the first card is a jack. There are 4 jacks and there are 52 cards. But once you take that first card, you will only have 51 cards left to draw from. And if you take one of the 4 jacks, you only have 3 jacks left to get. So when we multiply that together, we will get 12 over 2652. And as a decimal, that is 0.005. All right, let's look at number 5. So this will be our final example for this video. According to the Mars Corporation, M&Ms are produced according to the following proportions in relation to color. 24% blue, 20% orange, 16% green, 14% yellow, 13% red, and 13% brown. Assuming that your bag of M&Ms follows this trend, calculate the following probabilities. So part A, probability of selecting an M&M that is not blue. So if you add up all the percentages, you will see that you have 100%, which makes sense. So if 24% are blue, you can do 100% minus 24%, which is blue, to get 76%. So that's how many are not blue. So the probability of selecting an M&M that is not blue is 76%. See, it doesn't tell us how to write our answers, so I guess we can do, decimal form. Or you can say 76%. Okay, select the probability of selecting an M&M that is orange or yellow. So orange is 20%, and yellow is 14%. Let's see, let's just do this. 20%, and yellow is 14%. So we would have 20 plus 14 is 34 options out of 100. So percentages, you can kind of think of these as numbers if you want out of 100. So that's kind of how I would do it. Since they add up to 100, you can just assume that you have 100 M&Ms. And if you do, that means 24 of them would be blue, 20 would be orange, 16 would be green, etc. So then you can just make your fraction. So if there are 20 orange and 14 yellow, and those are both favorable events, then we could add those together to get the 34 out of 100. And I could write that in lowest terms, or I could write it as a decimal, 0.34. Part C, find the probability of selecting 2 M&Ms that are both red. So there are, 13% red. So that means 13 out of 100 are red. So the probability of selecting one M&M that's red is 13 out of 100. If I take one of the red M&Ms, only 12 are left, and only 99 M&Ms are left. So I would multiply those together. So 13 times 12 would give me 156. 100 times 99 would give me 9,900. And then I could just divide to get a decimal, 0.016. Okay, part D is find the probability of selecting 3 M&Ms that are all green. So green, 16%, so 16 out of 100 chance of the first one being green. And then the second one, since you've taken one green M&M, there will now only be 15 green M&Ms to choose from, and there would only be 99 total M&Ms to choose from. Now we've chosen 2 green M&Ms, so it would go down to 14 out of 98. And we would multiply those together. So 16 times 15 times 14, that would be 3360 over 100 times 99 times 98, that would be 970,200. And I could simply divide those two to see what I would get. That would be approximately 0.003. Okay, part E, find the probability of selecting 3 M&Ms and none of them are green. The way I would think about this is that each one has to be non-green. So if 16 out of 100 are green, then we can do 100, let me use black again here. We can do 100 minus 16, and we would see that that means 84 of them are non-green. So if the first one is not green, you have an 84 out of 100 chance that the first one is not green. Now we've taken one of the non-green M&Ms, so there are only 83 left. And then we'll take another non-green M&M, and there will only be 82 left. If we start with 100 M&Ms, after we take the first one, we'll have 99 M&Ms left. And after we take a second one, we'll have 98 M&Ms left. And so we will just multiply those together to get our solution. So 84 times 83 times 82 gives us 571,704. And 100 times 99 times 98, we found above, is 970,200. And when we divide those, we get 0.589. So that's the probability that none of the M&Ms are green. Okay, part F is selecting 3 M&Ms and at least one is green. Now, you might have made the mistake and thought that D and E are complements, because I was going to say that and then realized that's not the case, right? It's not they're all green or none are green. It's that they're either all green or at least one is green. Those are actually the complementary events. So D and F, these two are complements. So since these are complements, you can use that to your advantage and simply do 1 minus the, I guess we can do the decimal form, 0.003. And when you do that, you get 0.997. That would be the easiest way to do that one.